Okay, so two clusters of lightning talks. The first one are 6 different interesting projects surrounding the topic of accessible and interactive design. So the first 2 speakers will join us remotely, delivered to pre-recorded presentation. So the first one is titled Noteworthy, Investigating Touch and Speech Input on Smartphones for Personal Data Capture, delivered by Yuhan Luo. So let's watch the pre-recorded talk together.
This is Yuhan Luo, a recent PhD graduate from the iSchool at UMD. I'm presenting this work, Noteworthy, Investigating Touch and Speech Input on Smartphones for Personal Data Capture, on behalf of my collaborators, Bongsheng Li, Yanghu Kim, and Enkang Chen. Self-tracking has become a prevalent practice for people to track many aspects of their life. Therefore, it often involves capturing multiple types of data at the same time. In tracking daily activities, for example, people may capture the time, location, the activity type, and how they feel. Many of this data, especially subjective contextual information, need to be manually collected, and the action of manual tracking is important for raising self-awareness. Traditionally, people use touch input on smartphones to perform manual tracking. It's fast and easy for single or multiple taps, but can impose heavy input burden for text typing. On the other hand, speech input, with its fast and expressive nature, shows the potential to lower the data capture burden while collecting rich details. But little work has been done to see how it works with touch input to support self-tracking. In this work, we combine touch and speech input as a whole to capture multiple types of data. We developed Noteworthy, a multimodal self-tracking app integrating touch and speech input. With speech input, people can use local speech, which we refer as LS, to capture one data field at a time. By pressing on the little Mac button, for example, people can capture their break duration by saying from 11 to 11 a.m. They can also use the global speech, which we refer as GS, by pressing on the Big Mac button and say, I took a break from 11 to 11:10 a.m. to go for a walk, feeling great because, and then the system will automatically match the key information into corresponding data fields. With Noteworthy, we aim to answer 2 research questions. How do people use touch and speech input individually or together to capture different types of data for self-tracking purpose? And how does the input modalities affect the data richness of free-form input? We deployed Noteworthy in the context of productivity tracking for 2 weeks, during which participants were asked to log their data in 2 diaries, productivity diary and break diary, that consist of different data types. Due to the interest of time, I'm sharing the findings collectively at a high level. The usage log shows that touch input was preferred for structured data, including time, multiple choice, and Likert scale, while speech input were preferred for time span and text. Participants like to start with GS first and make individual adjustment with LS or touch if needed, and as they found global speech input was fast, intuitive, and close to natural language. Also, GS was used more frequently in break diary than the productivity diary because all the data fields in the break diary were on the same screen at once. The result of qualitative coding, we identified 3 categories of richness level in free-form text, including generality, specifics, and specifics with additional context. Using logistic regression, we found that entries involving speech input tend to be specific and were more likely to include additional contexts. From the study, we were excited to see that people adopted all the input modalities we provided in different scenarios. Going forward, the study shed light on future research opportunities to support efficient multi-data capture and extending the accessibility of in-situ data collection research to special groups. The paper is still working in progress. If you're interested in knowing more, please stay tuned.
Really interesting work. So if you have questions, unfortunately, I think Yuhan won't be here for the poster session, but you can find her contact information in this handbook under the poster change page. Okay, so the next one, again, is another work titled Promote Inclusion Through Users Selected Materials in Participatory Design, delivered by Selma Al-Sayed Ali.
Promoting inclusion through user-selected materials in participatory design. I'm Selma, and this is joint work done with Dr. Beth Bonsignori and Dr. Joel Chan at the iSchool. In the design of systems and technology, users are oftentimes ascribed the materials to design with, from colored sticky notes and markers to microcontrollers and tablets. However, this imposition of materials can be quite problematic, as these materials are oftentimes not situated in a context relevant to users. Materials, no matter how unsophisticated they may seem, are embedded with values, assumptions, and sociocultural associations. When these are not aligned with the user's norms and values, it can lead to the undermining of the user's lived experience, expertise, and situated context. Thus, it is important to be mindful of the materials selected when designing, especially when designing alongside marginalized users. Previous work has shown some of the pitfalls of imposing certain materials on users. For example, in their work with lower-income African-American older adults, Harrington et al. Found that the adults felt belittled and skeptical when using ideation materials like sketching paper and colored pencils. In another example, Smith et al. Found that youth in Namibia were hesitant to bring in physical objects to represent the effects of colonialism in their lives, and instead opted to bring in personal narratives and memories to use as springboards for their designs. From these examples, we can see how it might be useful to give users more control and flexibility over the materials they design with. In this work in progress, we are interested in examining how we might enable people to bring in their own materials to design with. What sorts of materials do users bring in? How do users incorporate their materials and others' materials in their designs? While we may think it's a simple matter of telling users to bring in whatever they want to design with, in practice, there's a lot more considerations that need to be taken into account. Systems must be set in place that guide partners on what to bring in, how to make use of what they brought in during the session, and the system must support both tangible and intangible materials and artifacts. To address this need, we are designing a system to scaffold the process of users bringing in their own design materials, and then using these materials to collaboratively refine the design problem and co-design solutions. Our current version of the system consists of a shared digital canvas with multimedia support and a series of participatory activities that build on one another and draw on tangible and intangible objects users contribute. We instantiate this system through Padlet, which provides multimedia content support, collaborative real-time editing, and is accessible via web and mobile. First, the system instructs users before a design session to upload things they are interested in using to design with relating to the design problem. Second, users work together to find connections between what they brought in and what others brought in. These connections are noted down as tags, as you can see in the PowerPoint. Third, users collaboratively come up with design requirements or key considerations to keep in mind when designing solutions to the design problem. These requirements draw on the tags and materials from the two previous activities. Fourth, and lastly, users ideate solutions and then have the opportunity to share their solutions and exchange feedback with their peers. We tested our early system with 2 graduate students in a pilot study focused on creating tools for cultural heritage preservation. Come and talk to me to learn more about what happened exactly during this pilot. We plan to continue evaluating the system in a series of case studies focused on cultural heritage preservation and Internet of Things. This will help us to gauge the effectiveness and transferability of our system across settings. Thank you.
Okay, for the next one, we welcome our first in-person speaker for this session, Zhou Yan from UND Computer Science Department, and he's going to talk about interesting projects titled FibeHedral.
Hi everyone, I'm Zhou Yan from Small Artifacts Lab Computer Science, working with Professor Huaishu Peng. And then my main research area is digital fabrication. So today I'm presenting our paper from WIS 2021, Fab Hydro, printing interactive hydraulic devices with a affordable stereolithography 3D printer. So with current advancements of 3D printing and the price drop of 3D printers, you can print a lot of interesting things fairly cheaply. You just need like a cheap printer, some filament, or in terms of stereolithography, some resin, and then you can get fairly dramatic form factor outcomes and some with, to some extent, usefulness. For example, the battery holder and the pen holder. But what is really missing in a lot of like available files and the workflows in 3D printing is functionalities from the end product, and especially mechanical movements. So to take it one step further, we revolve this project of try to build in hydraulic actuation system with a cheap stereolithography 3D printer. Basically trying to articulate that by retrofitting existing 3D printer workflow, we can embed more interactivity in the outcome. So in this project, we proposed two printing processes, and one is called submerged printing. And in this, on the left-hand side, so basically in this process, we make sure that the entire build volume is submerged in the resin while the printing is going on. So intrinsically, all the chambers in the design will be sealed with resin in it as hydraulic fluid. So with flexible material, we can get a really neat hydraulic actuation system with the structure designed like that directly off the printing bed with minimal post-processing. But there are a couple of challenges we can't fully eliminate with this process. For example, we're still slightly modifying the printer. And then the other is that there is still a slight chance of the part rupture and releases the toxic resin. So we propose a second method to output the equivalent without hardware modification, but more post-processing, which is printing with plug. And the outcome would look like something on the right-hand side. Obviously, it could be much more complex. This is just an example. And then we propose a plug and connector interface so that the user can print the actuation system hollow and fill in the hydraulic fluid of their choices, and then seal the part with the plug. And one bonus would be like you can construct subsections of these and then construct and then connect them together after the print to construct a bigger hydraulics actuation system. So to make the design flow smooth, we propose a design space with design guidelines and parameters for the end user. And then these are presented in a way how hydraulic systems are conventionally set up with generator, transmitter, and actuators correspondingly. So out of that, we designed a set of different actuation behaviors, elementary actuation behaviors on the bottom right corner. And then we have several applications. On the top left is a interactive game where like two players will collaboratively control a flexible stylus to catch fish on the iPad. And right top corner is a motorized phone stand, which would provide motion-based notification as an ambient user interface. And bottom left is a folding lamp, which would light up together with a controllable posture derived by actuation. So in all, the main takeaway is that we want Fab Hydro to be able to articulate that by retrofitting the conventional 3D printing process, we can easily achieve more functionality and interactivity in 3D printing. And then we have more projects coming up, so stay tuned. And I guess I'll wrap up here. And then for more information, you can refer to my website or our lab website. And then this paper with the same title is archived in the HCIL library. So if you need to check out more data and documentation of the implementation, you can go there. And that's all for my presentation. Thanks.
Thank you. So let's welcome the next speaker is John Hawley, from iSchool, talking about how people leverage self-tracking applications.
Good afternoon, everyone. My name is John Hawley, and I'm a first-year PhD student in the iSchool. I'll be presenting this research on behalf of my collaborators, Dr. Jessica Schroeder and Dr. Daniel Epstein. In this work, we wanted to examine how people actually went about looking for self-tracking apps and identify ways technology can better support the process. So with smartphones and mobile apps being more omnipresent in our daily lives, self-tracking apps have enjoyed increased attention over the recent years. Self-tracking apps are apps that allow people to track various aspects of their lives to gain self-knowledge, for example, such as tracking their food intake or their physical activities. We often use these self-tracking apps to achieve various personal goals. For example, here, Strava is a physical tracking app that can help an individual achieve their sports goals. Correspondingly, there are many research that study how self-tracking can be used more easily and is feedback more useful, but there is a lack of understanding of how people actually go about searching for these self-tracking apps and the problems that they face. This is a problem since we know barriers encountered during the early stages of self-tracking tend to cascade, making the overall experience negative to the person. For example, if a person were interested in learning about their nutrient intake, selected a food tracker that only tracks the amount of calories, it wouldn't be as helpful and lead to early abandonment. This problem is exacerbated by the sheer amount of apps that is in the marketplace today. Thus, we sought out to understand how people search for and select self-tracking apps and find ways to better support them. To answer our research questions, we first reviewed literature to understand what characteristics of self-tracking people have prioritized. We found that people cared about features that are related to self-tracking, such as the type of data that it captured, what kind of feedback it provides, etc. And then based on what we learned, we created a low fidelity prototype depicting an app store that surfaced these characteristics of self-tracking. The low fidelity prototype has common elements found in app stores, such as the product page showcasing the app and the store pages that shows different types of apps. We surfaced what we learned during the literature review by providing shortly worded tags to describe what the app actually does. And lastly, we conducted semi-structured interviews with 18 participants to probe what people considered during their search, how they search for their self-tracking app, and their feedback on the low fidelity prototype. We found three main findings. First, we found that people prioritize features related to self-tracking. For example, the type of data that is collected, feedback that it provides, and goal-setting capabilities. Second, we found that people often try out self-tracking apps. People tried out self-tracking apps in various ways. Some would input dummy data and others would input data as if they would be using it long-term. Lastly, we found that app stores that allow people to easily browse by features is helpful in finding and discovering what app would suit their needs. Lastly, based on our findings, we found that the selection process is not as clear-cut. People would continually assess if the app suits their needs, even after selection. So we also recommend self-tracking app designers to design with data portability in mind, meaning that it would be more helpful if people were able to transfer the data between apps. And lastly, we recommend app stores to have a more easy way of showcasing self-tracking app features and browsing by them. Thank you for coming to my talk, and I welcome you to visit my poster so I can take more. This work has been published in ACM InMut December 2021. And I'd like to thank Dr. Daniel Epstein from UC Irvine and Dr. Jessica Schroeder from the University of Washington for their help, and our research and pilot participants for their helpful feedback. Thank you.
And the next one, our accessibility guru, Jonathan Lazar, talking about ways to make PDF forms accessible.
Hi, I'm Sparsh Paliwal. I'm a part of the Trace Center here at University of Maryland. And today I'll be presenting Formally, which is a tool used to make PDF forms accessible. There are trillions of PDF documents in this world. However, only a fraction of them are accessible. Why? Let's look at this picture towards the left. To make a document accessible, it needs to be taken through a process of tagging, and then it turns into something like a document towards the right. However, this process is really expensive and takes a lot of time. So not a lot of people do it, and we end up with a lot of documents which are not accessible. Our team last year presented a tool which streamlined this process of making documents accessible. And this is the tool. However, it did not cover a particular use case, which was PDF forms. PDF forms are central to businesses and government processes. So for example, last year, people wanted to vote from home and they wanted to have accessible PDF ballots. Or like even the healthcare workers wanted PDF forms which were accessible. However, making PDF forms accessible comes with its own challenges. A PDF form is composed of smaller elements, essentially the fields which are there in the PDF form. To make just a single PDF form field accessible, you have to draw a box around it, define what kind of field it is. Is it a text box, checkbox? Then you have to define what is the label for it. And if it is a radio box or checkbox, you need to group them together. However, even though this might seem approachable, if I tell you you have to do it around 100 or 200 times in a huge form, it's going to be a really, really heavy problem. Another thing that happens with forms is that they are way too much dense, and for like doing any kind of operations on them can be really hard for a user. So we developed a tool which addresses all these challenges, and we named it Form LE. So I'm going to be showing you a demo of the tool. Okay, so here is the tool, and I have uploaded a 2-page PDF into the tool. Now, in the very first step, instead of expecting that the user will be using the whole form, we tell them, why don't you tell us a small portion which you want to handle at first? Now, instead of expecting them that they'll mark each and every field, we use machine learning algorithms to already detect all the fields and their types in the form. Unfortunately, these algorithms do not always return the right kind. So the user will quickly review, and if something is wrong, they'll correct it. So this descriptions is actually a text box, not a radio box, so the user will fix it. The same way, they'll go and review all the suggestions provided by machine learning algorithm and then move to the next step. Now, user will be doing the same thing for the label. They'll go ahead and review all the labels which are present in this form. Everything seems correct except this disabled veterans, which doesn't have a label, so user can create a label for this. And looks all good. Now we are safe to move to the next step. In the final step, user can actually see that these are all the checkboxes which needs to be grouped together, and they group them. And also we need a label for this group. So they label it, and we seem good for this step. So we are done fixing this section. So we'll proceed to the next section. And now again, we can select how much soever section we want to fix at once and proceed to the next step. So there is another special thing which is happening when we are moving between sections. So user, because they have fixed different things in a particular section, our machine learning algorithm can actively learn what are the mistakes which it did in the previous section and fix those. So with each section, the recommendations that the algorithm or that the model provides improves, and that's a great part about going section by section. Now, finally, till now, we have done the whole problem discovery. We did the user interviews and some pilot studies based on which a lot of designs which you saw in this tool were backed by. And obviously, we are done with the designs, and this was the initial prototype. In future, we will be integrating the machine learning models. Right now, whatever you saw were the mocks. And obviously, finally, we'll be user testing this tool. And yeah, those are our next steps. And finally, I'd like to thank Adobe Research and National Institute of Disability for supporting this research. And yeah, thank you for listening.
Okay, so now we're at the last talk for this session. Let's welcome Yuexi Chen from CS, introducing an interesting project titled Dog Dancer.
Hi, everyone. I'm Yuexi Chen. Today, I'm going to talk about Dog Dancer, an authoring tool for creating ultra-responsive documents with layout recommendations. Nowadays, people spend time on all types of devices. Responsive design means retargeting layout to adapt to screens of different devices. However, there are also other factors that may influence layout. For example, for users with low internet bandwidth, we may want to display fewer images. And for different customer segments, we may want to display different content. Unfortunately, if we consider a lot of factors, it will result in combinatorial explosion. Suppose we consider 3 devices, 2 types of image ratios, and 2 customer segments. That will result in 12 designs. In current designer tools, designers have to manually create multiple versions. In prototyping tools like Adobe XD, and the process is very laborious and error-prone since they have multiple versions to maintain. Designers can also try to use template-based approach. There are commercial website builders like Webflow, Squarespace. However, most of those templates are predefined, and it's very difficult to explore different design alternatives since you need to try out different templates one by one. We propose a novel authoring tool called DocDancer. Our design goal is to reduce manual editing in creating ultra-responsive designs. We also want to preserve the expressiveness in layout authoring and also improve the version management experience. There are 2 major features in DocDancer. One is responsive layout recommendation, and second one is content alternatives. Let's watch a demo. Okay, let's add an image to canvas. Let's create a group of 2 images, a group of 3 images. Now the layout is not specified. And let's check the recommendation. The first one is a grid layout. Let's add it. Now this is a tab layout. This is a carousel layout. Okay, we decided to choose grid and carousel. And let's set the active region of carousel layout 400 to 900 pixels. Let's preview the canvas. It's a carousel, still a carousel, great. We can also create content alternatives. Suppose we want to create alternatives for this gift card offer. Let's replace with an airline discount. Let's choose a layout by clicking the arrows. Okay, let's choose this layout. Now we have 2 alternatives. Let's name this vector. It's called customer. It has 2 options, new customer and existing customer. Let's bind the first alternative with new customer and then second one with existing customer. Instead of copying and paste the whole canvas, we just use a radio button to control different local alternatives. So this is the demo of DocDancer. We also conducted a user study. In the comparison study, we compared DocDancer with Webflow. Webflow is a popular commercial responsive website builder. It has more than 3.5 million users worldwide. We recruited 16 participants, and each participant is asked to reproduce a responsive design in both DocDancer and Webflow. In the second round of user study, we also tested advanced features of DocDancer, including create content alternatives. It turned out that designers spend much less time in DocDancer than Webflow, and they also spoke highly of the features in DocDancer. One designer said about the responsive layout recommendation feature, switching between different patterns is easy. It's also non-destructive. I don't need to delete or recreate, and I don't have to think about which layout I want to use beforehand. I can preview all different options before I make the decision. And another participant also said, I like the idea that you don't need to create a new canvas and copy paste everything, but just change the image and text. So that's a brief introduction of DocDancer. And I'd like to thank my PhD advisor, Professor Liao Zhicheng Liu, our collaborator Nicholas from iSchool, and Vlad and Chris from Adobe Research. Thank you.